Okay, so welcome to the last day of the class of Summer A 2021. Congratulations. I think it's too early to say that. We have to wait until final exam, but you're almost done, which is good. So let's just take a look at updates to begin with here. There's no new update, but let's just review some important things. Please don't forget about end of the summer session announcement here. You have to do end of the summer semester or summer session course evaluation. This is due Friday noon. Okay. Now, end of the semester evaluation link is open until midnight of the study day Friday, but after 12 noon, I'm not going to give you those gifts. Okay, you can still participate, but please don't forget, please complete before noon Friday. If you complete end of the semester course evaluation before noon, okay, before noon, not afternoon, on Friday, number one, quiz 3B score becomes 10 out of 10. Currently, you probably have no score in it, okay? And also, you can ask me to drop one more bad score of the quiz, okay? Suppose you have like a 2 out of 10, 0 out of 10, 4 out of 10 quiz scores, I can drop that. Okay, so please follow through this procedure here. Very simple procedure. And here is the end of the semester policy. Please read through it. Okay, so this is very, very important. And today is the last quiz of 3C. And Monday, June 28th, 8 a.m. until 10 a.m. Final exam right here in this classroom. It's going to be 2 hours exam. I'm thinking of 5 problems, but I don't know. I can possibly do like up to 7 or 8-ish problem, but I think you probably prefer to have more time per problem, I guess. So I still probably thinking of going 5. I think we did, how many problems for midterm? 4, isn't it? Yeah. 4 problems for 90 minutes. You had plenty of time, I hope. No one, at least I noticed, that you wrote down very, meaningless comment. Oh, I'm running out of time. I mean, every time student writing, run out of time kind of thing, I just simply ignore. Because, yeah, too bad. But if I see more and more that kind of comments, that means, well, problem versus required solution time versus given time is kind of getting closer. So 4 problems out of 90 minutes was probably more than plenty, I think. Okay, so 2 hours, 5 problems, I guess. I don't expect any complaint about running out of time. Okay, so please study hard, and then all the problems are very similar to classroom example or homework, something like that, because I basically create the problem, cut and paste. I'm too lazy to create something new. So at least I'm going to use the figure, even though I can potentially completely reword everything, turn it into like a practically speaking different problem, but I still use the same figure. Okay. Do you have any question about the final exam, which is coming up on Monday, 8 a.m. right here in this classroom? And also don't forget about end of the summer course evaluation, which is due Friday, 12 noon. Now, please be careful. You can still turn in email to me. I just basically don't respond. Please complete and turn in email request before noon on Friday. Okay, survey itself is open until midnight, but I just basically cut off 12 noon. Any question? Okay, so today is the last day of the lecture, and then right after today's lecture, we're going to do a quiz. Go ahead.
How are we going to see the final grade?
You can't see it.
Oh, we can't see
well,
it.
Yeah, it's written, yeah. Let's just go over it. Okay, final exam. Okay. The final exam result will not be returned or reported back to you. Sorry. After your completion of the exam, Dr. Hayashima is no longer willing to answer any question regarding your grade of the semester. That means you never know. So you have to wait until the records office posts your transcript. That means everything becomes official. Then you know. Then you go like, yeah, I got an A, or my goodness, I got F. What? But it's official. Okay. So okay, that's what's written. The point is being, if I don't do this, quite frankly, everybody tries to know. Okay, what is my final score? Did I get A, or am I B still, kind of thing? Can you give me passing grade because I'm gonna lose my scholarship? All sorts of things, you can name it. I don't want to deal with, because grade is grade. Go ahead.
So our current grade, like on campus, isn't accurate.
It's accurate because it's based on whatever you did so far. It's a running course grade. So, but don't trust it because it's running course grade. If you completely screw up final, that could potentially completely change the letter. Right now, I hope you have at least the first 3 letters of alphabet. If not, you're in trouble. Okay. I really hope. I have no intention to flunk anybody. I mean, students typically flunk themselves out. No matter what I say and do, they want to fail. That's usually the students really fail this class. Okay, any other question? So you can see your Canvas gradebook until midnight of Friday. So after midnight of Friday, I basically close out that gradebook. Okay. So at that point, you have no choice, just to study, do your best for final, and then wait until the transcript shows up. Okay, summer is over, so it's just to get it done. Okay.
Do you know when they update the transcript?
I don't know. I just do my best. Okay, so if it's up, you know. Okay. All right. So remember yesterday we did the class example 441. Okay. So this is the moment of inertia of this entire cross section made up by 3 different parts composite body. And then we wanted to know the moment of inertia about IY prime. That means moment of inertia about this Y prime axis. This is happen to be centroidal axis. So this Y prime coordinate goes through the centroid, and this X prime axis goes through the centroid. So this X prime Y prime is centroidal axis. So first step you need to take for this problem is, okay, where is this centroid anyways, measured from this starting reference point? So you can choose any reference of your cross section. In this case, right here is a reference line. You measure everything from here. Then first thing you need to be doing is, okay, so where's the centroid, X over bar? So you did, okay? So you determined location of centroid, X over bar, right here, 68 millimeter measured from this line, which is Y-axis, okay? Then after that, you're going to find out moment of inertia IY prime, which is the moment of inertia about Y prime axis for this complete cross section, which is happen to be centroidal axis. Okay. Then of course you're going to create another table applying method parallel axis theorem. Yeah. So this is the parallel axis theorem for each part. Determine moment of inertia. Okay. This is very specifically the method I choose every time when I give you composite body programs such as, okay, determine the centroid location, determine moment of inertia, stuff like that. I'm going to force you to fill in this blank of the table. I'm going to probably preset the table for you, and then, okay, fill in the blank here, and then determine moment of inertia of this cross section given. Okay, so you have to stick with the method I cover in class. This could be very unique for any statics class. Perhaps other professors may not use this kind of table. This is something I started when I was undergrad student. Keep doing it. This is only way I can understand moment of inertia. Too bad you're taking this class from me. But this is a method. So a table is very specifically set up each different part, this is the area. Area is always specifically b times a. Base times height, always. The reason is if you deal with rectangular cross section, it's always 1/12 b cubed a or b a cubed, either way. B a, oh, that comes in. So I always stick with b times a for the cross section area. This is extruder. This is a local centroid for each part. If you choose a different cut for each different part, suppose if you happen to choose, okay, this is 1, this is 2, this is, we can do that, but every time when you choose different part, the value will be different. However, the end result should be the same, of course. That's the beauty of this method. And so having said that, let's take a look at today's example here, okay? So let's just go down to class example 442. Determine the moment of inertia of the beam's cross-sectional area about x prime axis. Wait a minute. Ooh. What's this? Deja vu? I think I thought I did it. Wait a minute. What's going on? This one is about x prime axis, not y prime axis. So what's the difference between this one and the previous solution? Can you use most of the information, I mean, we developed in the previous problem, right? I guess. So here we go back to this page, page 11. So essentially, we are going to use the same exact information about part 1 and 2 and 3 and area of each part. Now, you don't need x. Now, in this case, y tilde and y tilde a needs to be computed, right? Right. Now, what is the big difference here? What is y tilde? So one thing you realize is, wait a minute, so this x prime itself is centroidal axis. We know that. We don't need to find this kind of stuff. We know this, right? We know this. This is already given. Y over bar, it's 80. So x prime is already centroidal axis, okay? So we probably don't need any of those, but we can still use the information of area, okay? So let's just go ahead and do the same thing, okay? So I'm going to probably use information which is area of each part. And then I'm going to construct this moment of inertia computation table for the value of Ix prime. That's the only thing I do. So let's just go down here, take a look at it, okay? So I'm going to once again construct the table. Okay, just zoom in a little bit. Okay. So it's just the exact same part, 1, 2, 3. And what you need here is magnitude of dy. Plus or minus, it doesn't matter because we're going to take square anyways. This is a millimeter. So by looking at this figure, okay, so once again, I'm going to cut out the same exact part. Okay. So this is part 1. This is part 2. Here is part 3. And then, of course, each part has its own local centroid. Right here, right here, right here. And then the question being asked is dy. That means measured from centroid. What is this? For part 1. Obviously, part 2, here is the centroid of this part 2 is right here on the x prime axis. So this is I know that. How about this and that? One is positive, one is negative. It's the same value, right? What's magnitude here? What is dy?
60.
60, that's right. So both 60. One is plus, one is minus, but I don't care because we're going to take a square anyway. So I'll just take the magnitude, okay? Good. That's right. And then each part, I'm going to find out Ix prime over bar. So this is a local moment of inertia of each part, which is 1/12. This is rectangular cross-section B times A cubed, okay? So you can basically pick up the information of previous table. 1/12 base is 160 millimeter times height is 40 cubed, right? The unit is millimeter force. That's the moment of inertia. So this is 1/12 40 times 80 cubed. This is 1/12 160 times 40 cubed. So keep in mind, this is flip-flop because in previous problem we did Iy prime, which is 1/12 b cubed a. This is Ix prime, so this is 1/12 b a cubed. Slightly different. But anyways, rectangular cross-section. Where does that equation come from? Let's just review. Okay, so this equation comes all the way from here. Okay. So basically, I'm using this now. Now, previous problem, we used this one. Okay, so this is the moment of inertia of rectangular cross-section of base of B, height of A, about centroid. Okay, I'm picking up this equation from here. So that's the local moment of inertia of each part. Okay, so if you compute that, this is going to be 8.533 times 10 to 5 millimeter force. This is 1.707 times 10 to 6 millimeter force. This is the same as 8.533 times 10 to 5. Okay, so now we are about ready to go for parallel axis theorem. So this is the part 1, which is offset this much distance dy from x prime axis. So you have to use parallel axis theorem. This one too, the same and opposite dy. This one is right here on x prime axis anyway, so you don't need to apply parallel axis theorem for this particular part, right? So what is the composite body's Ix prime? Okay, so this is the summation of Ix prime over bar plus A times dy squared. Okay, so this is going to be 8.533 times 10 to 5 plus area A of the part 1. I have to sneak look at here. Area of part 1. 6,400 millimeter square, area of part 2, 3,200 millimeter square. So I'm going to use those information here. Okay, so area A, 6,400. dy square, dy is 60 square. This is part 1. Part 2 is 1.707, 10 to 6 plus 3,200, dy is 0 square. So that means, hey, this whole thing is 0. Part 3, same as part 1, 8.533 times 10 to 5 plus 6,400 times 60 squared. So if you go through this computation, you are going to get Ix prime 49.493 times 10 to 6. Unit is millimeter to the fourth power. This is the moment of inertia of entire cross-section of this composite body about centroidal axis x prime. Okay. So it's essentially the same procedure, just a different direction. Okay. So if you take a look at this homework assignment here, wait a minute. Is this déjà vu? Wait a minute. Homework 441 is locate the centroid y prime and then ix prime. That's what you need to be doing in homework 441 and now homework 442. It's just a different axis. So it's kind of similar yet different problem and same process. Okay, same process. Now, before we move on, I have an interesting trick. I usually do not share this because, you know, unless you really understand what you're doing, this could be a disastrous mistake. So we have to approach very carefully. There is an easier way to determine moment of inertia for this cross-section, only for ix prime. Now, this is the unique cross-section. What's so unique for that? This is different from your homework assignment. This is your homework assignment. This is a cross example. Cross example, this is very unique cross section. What's so unique?
Symmetric.
It's one of those.
It's a wasp.
Wasp, yeah. Wasp is incoming.
Is it just circling?
Yeah, it's circling.
It's patrol. Patrolling something.
Yeah.
You just get a good hit on it.
Okay, good.
Oh my god, I hate
It's gone. Yeah. Sorry. So this is actually symmetric about x prime axis. Okay. If you have a cross section which have at least one axis of symmetry, you can actually bypass all of those things. Let me show you the bypass easier solution here. I actually wouldn't recommend because people actually think that, hey, I can do this for any situation, but it's not. So this is the situation that you have a cross section given something like this. Okay, so this is a cross section. And then this is a cross section which is completely symmetric about the x prime axis. This is a centroid. This is centroidal axis. So you can represent this is essentially, you know, this is equal to this solid rectangular cross section. You subtract another rectangular solid thing. Okay, so you can represent moment of inertia of ix prime of this thing, which is this is wait a minute. Yeah, this is actually sorry, 160 millimeter. It doesn't look like 160, but this is also 160, 160 millimeter both. Subtract this thing is 120. This is what, 80, isn't it? 80. So you can determine, so this is about this centroidal axis x prime. This is given by 1/12 BA cube. This is 160 times 160 cube. Subtract 1/12. This is 120 times 80 cube. This is actually much simpler computation. You can get the same value, 49.493 times 10 to 6 millimeter to the fourth power. So this is actually much easier way to find out moment of inertia of this cross section, because this cross section is kind of unique. Okay, you can subtract internal guts out just to subtract moment of inertia of that portion of the area. Okay, I don't recommend it. But I oftentimes, if I know I can do this, I'll do this because it's much easier. Okay. Now, obviously, you can never do this if you have an axis which is not lined up as an centroidal axis. So you can never do the same thing for IY prime, period. Don't do the same thing for IY prime. Okay, this is only IX. Cannot apply this for IY prime because we cannot do that. So that's why I don't actually recommend this, because people actually do that all the time. Oh, this is symmetric. Let's just subtract. Well, wait a minute, it's a different, wrong direction of a moment of inertia. You can't do that. Go ahead.
So, say like the centroid was aligned with y prime axis, and there was some symmetry around that. Would that be the only case we'd use the IY instead of doing IX?
The case you can do IY also is such as, suppose you have a cross section, okay, completely like a symmetric in X and Y. Suppose if you're given this kind of cross section, you can do IX and IY, both, subtraction, okay. But this case only in X direction, because in Y direction it's not symmetric, okay. That's right. So you can do that if so. Okay. All right, next page. So this is a homework, of course. This is too bad. This is not symmetric in any ways. So you have to do a table method, create your own table. Actually, standard table, which we just did in class. This is the table to compute moment of inertia using parallel axis theorem. And this is the table you need to determine, if necessary, the centroid location. So you typically need two tables. One is to determine location of centroid. The other one is to determine moment of inertia using parallel axis theorem. This is rock solid standard, so please expect to give you this kind of table question. Okay, fit in those. Okay? So it's important to do your homework exactly as it's shown. Exactly like this. Please do that. Okay? Okay. So next page, let's just take a look at the cross product of inertia. Product of inertia IXY. Okay. Okay. Do you remember the definition of IXY? IXY is integral over the area. Okay. dIXY dA. So this is the product of inertia. Obviously, product of inertia of the area is going to be zero if the area has at least one axis of symmetry. In this case, this is the area, there's no such a thing, so product of inertia is non-zero. Okay? So let's just find out product of inertia, very, very similar to what we did to find out moment of inertia anyways. So you have two options. One is, of course, you're going to choose the arbitrary distance x and then cut out the very thin strip, dx, and then integrate from x from 0 to 1 inch. So that's the integration in x direction. You can do that. Or obviously, you can choose distance y, cut out small thin strip of dy, and then integrate from 0 to 2 inch of y direction, either way. Okay? So I'm going to choose this method, okay? So let me just sketch out. So this is x and this is y. All right. So I'm going to take the distance x and I'm going to take very thin strip, which is dx. So this is the area dA. Now this area dA has, of course, local centroid C. This is local centroid x tilde, y tilde. So this is local centroid. That's probably too thin. So this is the local centroid. And then, obviously, this is a function given. Function is what? Y equal to 2 times 1 minus x squared. So this is y as a function of x. And y tilde, local centroid y tilde is equal to half of y. And then local centroid x tilde is essentially equal to x. Okay? And dA can be represented by, so this is approximated by rectangular strip, which is dA is equal to y, which is this height, times the width dx, y dx. So dA is y dx. Okay. So now I'm ready to integrate to find out cross product of inertia. So dIxy is di over by x prime y prime. So this is a local product of inertia. Local product of inertia. Okay, plus dA times x tilde y tilde. This is parallel axis theorem, as you see. So those two added together is going to be dIxy from small tiny strip dA's product of inertia. So let's just figure out what it is, okay?
Can you explain how you got to this equation again?
This equation, it's coming from here. This is a parallel axis theorem for the product of inertia. Product of inertia is involving x and y. So moment of inertia is, this is like a dx squared or a dy squared depending on x and y. But the product of inertia a times dx dy. Because product of inertia is basically involving x and y both. Okay. So this is a parallel axis theorem of the product of inertia. Okay. All right. And then, so this Ixyc, this is local product of inertia of the rectangular strip. Like I said, product of inertia becomes 0 if you have at least one axis of symmetry. So if you take a look at previous page here, so you are talking about rectangular cross section, product of inertia is 0. Okay. So it's quite important if you go back here. It's actually quite important here. So you know what it is. What's this? So this is the product of inertia of this rectangular strip. What's that? 0. Important. Yeah, it's 0. Okay, so let's just figure out what it is. So, like I said, dIxy is equal to 0 plus dA is area, y dx. Okay, y dx is dA. X tilde is x, y tilde is half of y. Okay? So this is going to be 1/2 y squared x dx. Okay. So, okay, let's just continue here. So dIxy is 1/2. Now y is a function of x, so let's just plug in y equal to 2 times 1 minus x squared right here. So this is 2 times 1 minus x squared. Okay, 2 times 1 minus x squared, close bracket, square times x dx. Okay, so this is going to be, if you further simplify, this is 2 times x plus x to the 5th power minus 2 times x cubed dx. Okay, so now I want to have Ixy. Let's just integrate over the area A dIxy dA, in which this is essentially, in this case, integral in the direction of x dIxy dx. This is all simple function of x. So you can integrate in the direction of x. So this is integral x equal to, from where to where? X equal to from 0 to 1 inch. So x equal to 0 to 1 inch. Dixy is 2 times x plus x to the 5th power minus 2 times x to the cube dx. It looks like you can finish up this integral. This is 2 times x squared over 2 plus x to the 6th power over 6 minus x to the 4th power divided by 2. Evaluate it from 0 to 1 inch, which is equal to 0.333 inch to the 4th power. This is the cross product of inertia of this cross section. Okay. So too bad, sometimes, occasionally, not often, you have to deal with non-symmetric cross-section. If you design such a thing, of course, you have to handle with the product of inertia. Suppose if your spacecraft is completely non-symmetric kind of shape. My goodness. Suppose if that's the shape of spacecraft, if you attach the thruster here, what kind of spin are you going to get? Is it going to spin around this axis? Now, suppose if you all of a sudden want to spin this direction, how much thruster do you need? Where is the location kind of thing? You have to have those properties of non-symmetric volume or body. Now, typically, this is rare, because who's going to create the door like this? I mean, not many people. I mean, door is usually rectangular door. Maybe if you want to minimize your trailer of a camping trailer, with a teardrop shape and door is like teardrop shape. Well, what is the product of inertia of this cross section? You can pick it up your calculator and compute. Okay, anyways, but it's rare, of course, right? So this next page is homework 443. Determine the product of inertia of the shaded area with respect to the x and y axis. So obviously, you can do two ways. Obviously, you can integrate in x direction or y direction, taking a small tiny strip, either dx or dy. Okay. So it's a very similar process. Please do it by yourself. So the last page. Whoa! Congratulations. Last page, homework 444. Determine the product of inertia of the cross-sectional area of the C-channel shaded area with respect to x prime and y prime axis. What is the answer? I mean, I know the answer. Well, I know the answer. I know, I'm not going to tell you the solution, but I know the answer instantly.
0.
0, yeah. Why? Well, because this is the cross section which has one axis of symmetry, which is x prime axis. So what is the cross product of inertia? It's 0. 0. So when I want to see your homework solution here, I know the answer. So if you do this, oh, this is 0, This is not the solution because I told you today, I want to see your solution process to get this result. Let me take a look at the solution idea. I know the answer, this is 0, but that's the answer, that's not the solution, okay? I want to know the solution. So let's just take a look at this 444. So this is the solution 444. Okay, as usual, you're going to cut this composite into 3 parts, part 1, part 2, and part 3. You're going to create the very similar table in which we've been doing for moment of inertia. So you're going to find out the local product of inertia. Of course, it's all 0. Rectangle, rectangle, rectangle. Cross product of inertia is all 0, yes, fine. But you have to find out dx dy because you want to apply parallel axis on it. Okay? And then you basically do the same thing. Summation of all local product of inertia plus parallel axis based on dx and dy and cross section A, it should be 0. That's why this is 0. Now, by the way, I kind of knew it because if either the x or y axis is an axis of symmetry for the area, the product of inertia for the area is 0. We know that, but you have to draw the conclusion by doing computation. This is what I expect. Okay? So please do not be lazy at the very end. Of course, guys, the homework is, oh, it's 0. We know that. 0, that's it. No. You have to prove it. Too bad this is engineering, so too bad this is engineering. I'm a Japanese Toyota engineer. I'm sorry about that. Used to be. I'm American now. I'm kind of getting sort of changing into this country's sort of culture. Or, you know, whatever kind of culture. But anyways, I used to be Japanese. I cannot be American. Too bad. I'm a US citizen, but I'm Japanese. So it's so convenient. So every time when people say something, oh, I'm Japanese, I don't know what you're talking about. And if if people say, oh, I thought you were Japanese, oh, no, I'm a US citizen, you know. So either way, very convenient identity crisis. Any question here? So this is it. I covered everything. Congratulations. Probably a little too high because you have to take quiz and then final exam is coming up Monday. Do you have any question? I hope you enjoyed. Don't forget, evaluate this course. Due is Friday, 12 noon. Okay. So let's just do quiz.
Can we use the handout?
Ah, yeah, I give you a handout. Don't worry about it. I have a handout ready for you. Okay. All right, I'm gonna stop recording. Let's do quiz.